Okay, welcome back to the morning session. Since I also gave one of the optimistic talks yesterday, maybe I can say welcome back to reality. We'll start off with three cosmology results. And the first speaker in the session is Mohr, who will tell us about galaxy cluster studies with largest cosmic surveys. Please take it away.
Thanks a lot. Thanks, everyone. Thanks to the organizers in particular for the invitation, and it is really a wonderful venue for this kind of discussion. Okay, so today I'm hoping to cover sort of course, there has to be some kind of introduction, but then two relatively new results. This one just appeared in monthly notices, the first cluster cosmology results from eROSITA, and then this second one, a new all-sky ICM-selected cluster sample, is something that we hope to submit soon. The work that I'm presenting is done by many people in my group, and Professor Yinan Chu, who is now at a university in South Taiwan, led this eROSITA cosmology effort. The other people, Matthias Klein, Daniel Hernandez-Long, and Sebastian Bouquet, were involved throughout. Whoops, this happened in the testing too. Okay, so halo mass functions can be used to constrain cosmology. So we have here a plot of, so we have a mass function plot here. We have the dn, dl, and m per cubic megaparsec plotted with a huge dynamic range here versus mass. And you can see the mass functions from a hydro simulation. This is a rather old result. And you can see that here's a redshift 2, here's redshift 0. You can see that over time, over cosmic time, these halos build up on all mass scales. And the clusters that we're going to talk about today are out here at the very end. One point I'd like to make already, and I'll hammer home throughout, is that if you want to use the halo mass function to study cosmology, you don't have to use clusters, but there are good reasons to use clusters. But whatever halos you use, you need to understand the masses. And that's pretty obvious from the dynamic range here. Okay, baryonic effects are important. Feedback redistributes the baryonic mass, which is 10 to 15% of the mass, as we heard from Bianca yesterday. And a survey of halos is telling us not just about the growth rate of structure, but it's also sensitive. Here's the redshift distribution of halos, sensitive to the volume redshift relation. Okay, so here, integral over all observable halos times the volume. And I feel like this is getting a little too loud. Anyway, maybe I'll try to talk more softly. It seems to work extremely well. Okay, good. One thing I'd like to emphasize, maybe touching base with Hiranow's talk coming up, is that the sensitivity to high K modes in P of K is different for this cluster experiment than for the cosmic shear experiments. And so clusters can potentially provide additional leverage to this S8 tension. Okay, however, we don't go out and measure mass functions. We measure galaxy cluster functions, observable functions. And we find these galaxy clusters using their observable rather than the mass. Even if we find them using weak lensing information, we're not directly selecting them by mass. Weak lensing is also an observable. So here are just some figures of what the millimeter wave sky might look like at very high resolution. You can see these little dark points are the clusters and groups. That wavy background is the primary CMB, sort of gives you a sense of why this SC is challenging. Here is a ROSAT all-sky survey image. These black points are the sources. In general, clusters are not resolved at the resolution of ROSAT, but they are partially resolved at the resolution of eROSITA. And that gives additional leverage to eROSITA analyses. And here is a galaxy image, multiband image of a cluster. Okay, so galaxy cluster mass functions can be used as cosmological probes. Shortly after the supernova discovery of the cosmic acceleration, Zoltan Hyman, Gil Holder, and I added this figure for Gil, but I don't think he's here yet, put together an argument that we could use the cluster halo mass function study or the cluster observable mass function study to understand W. And what you see here are split into volume effect and abundance evolution effect as a function of redshift in both cases. Plots of the number per redshift for different values of W, where the differences between these plots are of order 1. So this is like -1, -0.6, -0.2, so very large changes in W. And here is omega matter, which also is very sensitive. And these are plus or minus 10% effects. Anyway, this was a basic science driver for SPT. And then once SPT was funded for DES, it was a large driver for DES, and of course later for eROSITA. What I'm going to try to keep emphasizing throughout the talk is that the calibration of cluster masses is essential. And so for these modern surveys with the weak lensing data, there are really new opportunities in this experiment. And this was just the rest of the story. Here are constraints, omega matter versus W. Clusters by themselves, if you're just using the redshift distribution, we're just constraining some combination of those two parameters, but in combination with primary CMB and supernovae. The hope was you could constrain the dark energy equation of state parameter, which of course has been done since. That was 20 years ago. To give you a feeling for how this works, let me say a few words about how you model the halo observable function. Okay, so in the limit that a selected set of clusters, each selected object, can be mapped into a single collapsed halo, that's an important limit, which we can come back to and discuss over coffee. What you need is some mapping from the observable to the mass space. And these mappings exist. They're directly observed in the real universe. They're power law relations. You have to include the intrinsic and measurement scatter. And so basically to model, here's a halo observable function, the redshift distribution of an SPT sample, the signal to noise distribution, the mass proxy in the SC is a signal to noise within SPT anyway. To model this, starting from the halo mass function, you have to use some kind of observable mass relation of some general form. You have some amplitude, you have some mass dependence, you have some redshift dependence, typically 3 parameters, plus you have some intrinsic scatter. All clusters are not identical. There's a forgiven mass, there's a distribution of morphologies. And of course you have to include the measurement noise. So basically you relabel mass to observable, and you do some convolutions, and out pops the halo observable function. And we empirically calibrate, because of the importance of this observable mass relation, all of these parameters have to float while you're studying cosmology. And so a significant amount of information is used for that calibration. And again, gravitational weak lensing is really the step forward here. Okay, try to speed up now. That's sort of the introduction. So how does this work? Well, I wanted to start with our analysis from 2019, led by Sebastian Bouquet, pictured here. The data set was 343 SC-selected clusters from SPT. We had weak lensing data on only 32 clusters. Those were targeted imaging studies. We used an SZ mass redshift relation. So we had 4 free parameters when you include the scatter. And we basically used the Poisson likelihood. This is what our likelihood is. We cycle through the clusters. We know what the probability of finding cluster at a given signal to noise in redshift C is signal to noise. There's this term here, which is like an integral over that halo observable function. The modeling then accounts for the different selection biases, the most important being Eddington and Malmquist. And here is just an expression for the number density with respect to C and redshift, expressed as this integral. This is a Bayesian approach, and you can see the mass function, the halo mass function appearing here. Okay, so many of you are probably familiar with that, but some not. Okay, the takeaways of this analysis then, just jumping to the chase, is that the cluster data set is well described by our model. What do I mean? I showed this plot before, but let me emphasize now. The green region is the 1 sigma region allowed by the uncertainty by the posteriors and all of the parameters that we fit. And here's the redshift distribution, here's the Xi distribution. And you can see, and the data points are the histograms. These are 2 projections. And you can see that the data and the model are consistent. The cosmological constraints in this most interesting space today, sigma 8 versus omega matter, you can see the blue ones are the SPT cluster work. DES year 1 is back here. This little orange one's a little tighter. Kids, weak lensing. Back here, a little weaker. Here's Planck with neutrino masses marginalized over. And here's an older work from Weighing the Giants, Adam Mance and friends. And you can see, I guess the basic takeaway is that the cluster analysis cast in the way that I've just described provides constraints that are in good, that are consistent with other probes, including cosmic shear and primary CMB, and that the constraints are comparably tight. Okay, so this is encouraging. So now the talk, why largest cosmological surveys? Well, deep contiguous multiband surveys like DES, KIDS, or HSC offer major advantages to this science approach, to this analysis, this cosmological study. It requiring high significance red sequence counterparts, and I'll talk more about this through the rest of the talk, an optical counterpart for an ICM-selected cluster candidate removes contamination and allows you to build larger ICM-selected samples. So that's one benefit from large surveys. Weak lensing shear profiles directly, in quotes, happy to discuss that over coffee, constrain cluster masses. So these are the two major benefits of having large surveys. And when you replace DS, KIDS, and HSC by Euclid and Rubin, which is happening within this year in the case of Euclid, that should allow this science to be done much, much better. Of course, the weak lensing, cosmic shear will be done much better at the same time. I'd also mention here, I don't really say much about this, but it's important. Coordinated effort in numerical simulations, studying the halo mass function, studying the structure of clusters, understanding how that impacts the weak lensing mass estimates, all of that is needed to make the most out of these large cluster samples with the better weak lensing data sets. And over here, I just have a nice example that reminds me, these are the tomographic bins for DS year 3. What you gain from having weak lensing from one of these big surveys is there's a huge amount of effort focused on constraining the systematic uncertainties in the shear data. And then those results are primarily driven by the cosmic shear experiment. But then within the cluster community, you can use that information to carry out this other experiment. Okay, so a quick comment about Sebastian's upcoming work. We have an SPT-SC cross DS analysis instead of 34 weak lensing mass constraints. In this case, with DS, we have weak lensing mass constraints, weak, but weak lensing mass constraints on 680 clusters. And the SPT sample has been expanded to be about a factor of 3 larger. Validation on MOX is complete. Blinded cross-checks are ongoing. Looks promising. Sebastian hopes to unveil these results in a conference in June. What he was willing to give me was this little red contour, which is created from analysis of MOX that are informed by the actual new SPT sample and DES weak lensing. This is his 2019 result, and here is, if we're lucky, what the new result will look like. So it should be quite interesting and especially important in this issue of whether there's a primary CMB local structure formation tension. Okay, but the result I hope to present today, the first of the two, is the first results in eROSITA cluster cosmology. So we, or Yinan Cho, Professor Cho, led this result, but Matthias Klein, Sebastian Bouquet, and I were involved. What it is a test field of 140 square degrees called EFEDS, carried out by eROSITA early in the mission. The sample is 455 clusters after you do the optical cleaning. There's weak lensing data from HSC, public HSC data covering 177 clusters. Contamination is about 6%. If you just use the X-ray selected sample alone, that would be 20% contamination. So that gives you a sense of how much you benefit by using the optical counterpart information. We use pretty much the same approach as the SPT cross DES, but altered for an X-ray selected sample. So instead of signal to noise mass relation, we have an X-ray count rate mass redshift relation. 5 parameters. Yinan allows for the mass trend to evolve with redshift. There's no evidence that it does, but that's an additional degree of freedom. He also has the optical richness mass relation. And then there are some mass weak lensing versus halo mass free parameters as well. Okay, a complication is that the EFED's extent selected sample, these 455 clusters that we use, were selected using, they had to be extended sources. And therefore we had to model the incompleteness introduced between an extent selected sample and a count rate selected sample. Count rate is kind of like X-ray flux. And so we had to do that, and we were able to use this MCMF to identify the full cluster sample with resolved and unresolved sources, and compare that to only the resolved sources, and we're able to build a completeness model. And of course, we have a couple of degrees of freedom added to allow for uncertainties in that completeness. Here's the EFED sample itself, mass versus redshift. The black circles are EFEDs. You can see basically they extend to reasonably high redshift. Redshift 1 used to be really high for clusters. That's no longer the case. All the samples are pushing out that far, but it's low mass. So this is a small area, rather deep survey. Here's the redshift distribution of the sample. And in this case, this is the equivalent of the green that I showed you in the SPT analysis. This is the best fit analysis 1 sigma region from our preferred set of parameters. So you can see good consistency there. Here's the richness distribution of the sample, well fit by the model. And here is the count rate distribution of the sample. These are just 3 projections, but the basic picture is that the model and the data are in good agreement. In addition, the scaling relations, now I haven't shown you any scaling relations up to now, so this is perhaps important. The scaling relations are well fit by these power laws. So this is count rate. It's actually scaled count rate, so we can look at a particular redshift versus mass. You can see the gray region being the 1 sigma region, the dashed line being the self-similar expectation for those of you who follow that. Clusters are not self-similar. That's been known for 20 plus years. EFED sample just reinforces that. And these little points are the individual clusters with uncertain count rates and uncertain mass information. You can barely see that, but if you go to the paper, you can get all the details. And here is the redshift distribution collapsed into a single to the pivot mass in this relation. And here's the self-similar expectation. Here's the best fit. These are the data points. You can see there's really no tension between self-similar redshift evolution and the true clusters. Oh, and here are the same now for richness mass. You can see there's a lot of scatter, but we fit for the scatter using the data themselves. And here's the redshift trend. Also not much evolution in the case of richness mass. That's also been well known. What about the cosmological constraints? So you can get the details here. Important, I think, for this discussion is it's a full blinded analysis. So, well, that's become the standard, but only a few years ago it wasn't. The OK 2019 results were not blinded, but these are. And here we have the big blue region, that's the EFED's constraint, and several other cherry-picked. Well, there's the Planck constraint, you can't get away from that. DS3×2, which is the strongest cosmic shear experiment that's been carried out to date. And here's SPT-SE, our old cluster result. And you can see that in both the space of sigma 8 omega matter and S8 omega matter, the EFED's analysis with 455 clusters and 177 weak lensing observations of those clusters provide cosmological constraints that are in good agreement with these other probes, including the primary CMB. There's no evidence of attention. And the constraints are a little bit weaker, but not dramatically weaker. They're competitive with other constraints. So we're happy about that. So in the last few minutes, and I'm not sure how fast I go over this, I wanted to talk about something that we've been working on. Matthias Klein has been leading this effort. It's an all-sky ICM-selected or X-ray selected cluster catalog. So let me tell you about it. It should be on the archive in a matter of a couple of weeks. What we have is the legacy DR10 optical multiband survey over most of the sky. This is the galactic plane. And we have basically good data, not DES depth, but the depths were driven by DESI source selection in the north and somewhat in the south, and then many groups, including us, filling in with DECAM, the empty space. With that, we're studying, we have an X-ray survey. This is the ROSAT All-Sky survey, now 30 years old, and you can see the exposure map on the sky, and you can see the galactic plane. So we basically use all of the X-ray selected sources here and here, and the optical data that's available from the legacy survey to create a new catalog. And the Matthias has named it MARDLS. It covers 25,000 square degrees, which isn't all sky, but it's almost all of the extragalactic sky. And the sample at 90% purity has about 8,600 clusters. So it's rather large. Should be good for clustering studies because it's all sky, probes the largest modes. There are also subsets that are 5% contamination and 1% contamination that are, of course, smaller. Just show you a few characteristics of those, and then I think I have to close up. How do we do this? I think it's good for you to have a feeling for this, but it's described in detail in these papers. So what we do is along every line of sight towards a ROSAT source, 2RXS is the catalog we use. We use the optical data to search as a function of redshift for peaks in the red sequence population. And when we then take the most significant peak and assign that to the X-ray source with a richness, a redshift, an optical center, X-ray luminosity, and some first estimate of mass. We do this same analysis along lots of random lines of sight, which gives us the sort of random distribution of richness from the survey that you might expect. And then for each 2RXS candidate, we come back, and for its measured lambda and redshift, we can then, using these random lines of sight, we can quantify the chance that that particular matched optical X-ray pair is a chance superposition or a real cluster. And then what we do is we throw out all of the ones that are significant, that are low significance, let's say, that are likely to be a chance superposition, and that threshold can be tuned. And we have tuned it to create a 10% contaminated sample, 5% and 1%. Here you can see in lambda richness versus this X-ray mass estimator. In blue, what we have defined as the true clusters in MARDLS. In gray is the random, these are the random superpositions. And you can see that these are obviously random superpositions. These are obviously a different population, but there's this transition region where it's difficult. And we can't say for any given cluster here 100% whether it's a cluster or not a cluster, but we can say statistically very accurately what the fraction of false systems is. And here, just as an argument that we've done this before, we've used this for the EFEDS catalog. I just showed you that analysis. We're using it for the SPTSC cosmology sample. We've done some Planck studies. 2 minutes. Here is the mass redshift distribution for this sample. So you can see that the MARDLS sample probes the group range only at low redshift, as expected. The eROSITA sample will go deeper than this. And so basically this group sample will be probed out to a redshift of 0.4 or so. And the sample should be larger, except the sky is split into Russian and German sky. So we get an advantage there because we can use the whole sky. Up here is the same sample, but now the points that appear in either MCXC, a famous X-ray catalog, Planck, or ACT-DR5 appear colored in blue. And so basically 2,000 of the 8,000 MARDLS clusters are found in those other surveys. Here's a redshift distribution. You can see MARDLS as a rather shallow X-ray survey is peaked at low redshift, but it has this long tail. Okay. It's a nice sample. We looked at the cosmological potential. In particular, Daniel Hernandez-Long has looked at that using MOX. And we basically used the codes I've talked about from Bouquet and Cho, but now extended to follow the varying exposure time and background over the sky. It's a complication for an all-sky survey like this. We used a 99% pure sample, so we didn't have to worry about contamination. We have same kind of, we have an X-ray scaling relation, we have a richness galaxy scaling relation. We have a completeness function, we have 4 cosmological parameters, and the little red constraints here are forecasts. Of course, in a forecast, you don't know where you lie in this space. We can only forecast the size of the constraints. And we're excited that if this works out, we should have some very nice constraints, but I don't have them today. Apologize for that. Here's a nice large-scale structure map from 2 mass galaxies, and these little points are the Martles clusters within the redshift range 0.05 to 0.1, showing, as is well known, that clusters trace the large-scale structure quite nicely. So in summary then, deep multiband optical IR surveys offer major advantages to galaxy cluster cosmology. We're only getting started on that. And it's not just the weak lensing mass constraints, but also the larger ICM-selected cluster samples are possible if you combine optical with X-ray or optical with SC. Showed you some new cosmology constraints from eROSITA. They're competitive with other probes. They're consistent with other probes. They show no statistically significant evidence for an S8 tension. And the eROSITA sample itself, we hear that the cosmology analysis is proceeding rapidly now, should be much, much more constraining than what I've shown you with just this test sample. And I've then showed you an all-sky X-ray selected sample, has 10 times more clusters than EFEDS, 5 times more than the SPT cross DS project that Sebastian Bouquet is leading. So we think that'll be very interesting for cluster cosmology. But it's also interesting for clustering studies, for cross-correlation against other probes. And we're certainly very open to collaboration and would like to hear from you if you have ideas of how you would like to use this sample. Okay, thank you.
Thank you, Joe. Are there questions? I didn't know you had one too.
Yeah, hi Joe, nice talk. Actually, I have 2 quick questions. One is that when you are estimating halo mass X-ray, so whether it is R500, sorry, M500 or M200 that you are taking into account?
So you could do either one, but the weak lensing data are better suited to constrain M200, something at a larger radius. M500 was very popular when X-ray hydrostatic masses were the best we had, because as you know, typical X-ray observation only goes out to about R500. But with weak lensing, M200 is better. Also, the halo mass functions tend to be, there's a long history in the literature, they tend to be better behaved, more cosmology insensitive if you use M200 mean rather than M500 crit. So.
Yeah. And the second thing is that dynamically these objects are, varying in various states, like from really equilibrium to
yes,
can be anything. Yes. So how you tackle that issue?
Well, I think you can see that well, you can certainly see it in the simulations, but I am pleased to see it in the data. Here is the X-ray, think of it flux versus mass relation scaled to a particular redshift. And you can see it's not a perfect power law. They're scattered there. That scatter is driven by the departures from equilibrium, the asphericities of the clusters, all the complexity that we know is present in that population. So that's how we account for that.
Thank you.
Yep.
One of your plots. Thank you. Just when you write the dn dz with respect to redshift for these samples, is it implicitly averaged around some halo mass of clusters? Because
do you mean
right? Because the halo mass function would go down the whole way, right? So I was just wondering if there's a marginalization happening there.
So these validation plot. So in the analysis, we cycle through every cluster individually and use its location in redshift and observable, wherever that happens to be. So kind of like mass redshift. But for these validation plots, to make them, we haven't figured out a good way to do them in a more sophisticated, multi-dimensional format. And so we do projections. So this is, a projection along redshift of the count rate mass distribution. Sorry, this is, yeah.
No, it's probably a plot which was the green curve matching the data very well, which you showed somewhere.
Okay, thanks.
Yes, exactly. The first one there. Yeah.
There.
For instance, yeah.
Yes, so these are just two projections. So here we have integrated over Xi, signal to noise, to get the redshift distribution. And here we have integrated over redshift to get the Xi distribution. But in practice, the likelihood actually doesn't use these projections. It uses each cluster individually.
Thanks.
Hi, thanks for the really nice talk. So you've shown some interesting combinations of SPT times DES and eROSITA times other things. I know that there's also quite a big cluster sample from the Atacama Cosmology Telescope.
Yeah.
So do you think that the SPT cross ACT combination?
DS cross ACT, you mean? I'm sorry, please.
Yeah, I mean, either one of them could be a good data sample to analyze.
It should be fantastic. I mean, they have, instead of, in our cosmology sample that's coming up, SPT, I mean, CosDS, we have 1,000. They have 4,000 clusters. They have much more horsepower. They have the same, roughly speaking, weak lensing, because essentially all SPT clusters are also found by ACT, not perfectly one-to-one, but essentially. So it'll be very interesting to see that analysis. I can say that in this analysis, we're not weak lensing limited yet, so we would benefit from having larger numbers. So ACT with 4 times more clusters would be very interesting today, or tomorrow even.
If I may squeeze in one question, even though I'm chair, having battled a lot with projection effects in optically selected clusters, it's of course inspiring to see how robust you are with these other selections. Do you think it will still be the case for future analyses, or will you encounter similar issues when the error bars shrink?
I'm sure that it's hard to know exactly what the problematic cases will be. At the 1% level, we have, pre-merging systems. And do you count those as 2 clusters or do you count them as 1? That's not been an issue for us. We haven't spent time worrying about that yet. What we would try to do is look at how they've defined the halo mass function in the simulations and try to apply some kind of similar pseudo observational approach. That's one example. I didn't mention the optical cluster. I mean, I think there are additional problems with the optical clusters that don't face ICM-selected and optically cleaned samples. Yeah, I'd love to discuss that.
Yeah.
Thanks, Joe. So we looked at these 3 different ways to approach omega matter sigma at plane today. You talked about, and each one looked like competitive with Planck. And I wonder if you, in terms of this forecast, for example, I wonder if you have thought about combining these and then how will that forecast look like? And are there roadblocks to do that?
So there were roadblocks here in this analysis because the code that we had developed, that Enon developed independently, scaling from Sebastian's method, wasn't capable of handling W. And so there was, so typically it would be very interesting to combine any of these with Planck if they were consistent and then study the equation of state parameter, for example. We couldn't do that in this analysis. In our upcoming SPT analysis, we should be able to do this. If we're able to analyze this new cluster sample, we should be able to do that. That's very, very interesting. We also are looking at modified gravity models, F of R and NGGP with this SPT, not this sample, but the SPT cross DS. We're looking at some novel dark matter models where we can constrain the parameters. It looks quite interesting. Everything's, when you do these extensions, it quickly, you don't have enough information. And so you're driven to want to combine data sets as you have suggested.
One of the things that you showed is the X-ray scaling relations with mass and then the richness mass scaling relation that you take into account in order to get the cosmology constraints. Have you tried to see if there is a correlated scatter between these? And so that's one. And the second question is, if you do you have to worry about these issues that the halo finders in simulations on which the halo mass functions are based, they define the halos in 3D. while here it's not really 3D. And so how, like, at what point will it become important?
It's important.
And at what precision, right?
Okay, so on that second question, this is what makes, in my view, ICM-selected clusters more powerful than the optical selected clusters, because the X-ray signature comes from the virial region. The SC signature you can integrate over large-scale structures and you can get an SC signature, but it's temperature times density, so it's really virial region dominated. The optical signature is more spread out. So I think that is so we feel that these ICM-selected clusters can be mapped one-to-one onto the theory halos. And I don't think that problem has been solved for the optical yet. And the first question, yes, in all of our analyses for each scaling relation, like if we have richness, SC signal to noise, and weak lensing, we have correlated scatter allowed between all pairs of those. Those are free parameters. There is no evidence for correlated scatter yet. There's no preference, but we allow for it.
Let's thank Joe again, and thanks everyone for the good discussion.